One of the most common tasks in data analysis is to look at a dataset and determine a model that fits the data. One of the most common ways to do this in physics is by graphing the data and plotting a line or a curve, a parabola or sinusoid on top of that dataset in the hopes that the line goes through the data points, perhaps. This act of curve fitting is one of the most common forms of data analysis in physics. But to start, let's put things in context. What does data analysis in general actually look like? Well, in general, data analysis starts with some form of experiment or observation, some form of information collection that gives us access to, well, the data. That data then needs to be analyzed in some form or another. And the analysis leads to us to be able to, well, actually form some useful insight. The insight is the ultimate goal. What's the point of conducting an experiment or some observations if it doesn't actually tell us all that much in the end? So what do we mean by insight? Well, probably in physics, we're looking to be able to make some sort of meaningful predictions. If we understand how the system behaves based on the data well enough to inform a model of how the system is behaving, we can perhaps predict how the system will behave in circumstances we haven't yet observed. Perhaps we're, on the other side of things, trying to support or refute a hypothesis. We're trying to test that hypothesis. And the act of testing a hypothesis might lend support to this hypothesis, or it might totally disprove it. If we inform our model from which we're trying to fit to the data in the analysis process based on the hypothesis, and it doesn't work, well, that says something about the hypothesis. Or on a less physicsy side of things, perhaps we're trying to just help make decisions. Perhaps a pharmacy is interested in opening a new branch in a given location. They might make some observations of what the local population is, collect a data set, and analyze that data set to determine how likely that population is to purchase prescription drugs, make predictions from that about the likely revenue their new branch would perhaps receive, and make a decision as to whether or not it's worth it on that basis. Now, in physics, perhaps, let's go through a rough example. Let's suppose we're considering a relatively simple physical system, something like projectile motion. The experiment or observation under those circumstances might perhaps be a video of a thrown object. The information we would collect from that video would probably take the form of some measurement of position of the object as a function of time. Perhaps we're measuring the height, let's say y1, y2, y3, a whole bunch of different heights of the object as time rolls on. t1, t2, t3, etc. Now this data table tells us how the observations are related to the other observations. It doesn't tell us anything about the underlying model. Determining a model that fits that's the act of analysis. But in this case, if what we're talking about is projectile motion, the model is reasonably clear. We're looking for a mathematical function, y, that describes the height of the object as a function of time. And if this object is behaving as expected in, simple first-year physics type contexts, the model that fits this will be a simple mathematical function, something like an initial position plus an initial velocity times time plus half some acceleration times time. Now, what sort of insight we might get from this, well, really depends on the context. If this is perhaps a video of a thrown object in one of the videos of the Apollo moon landings, perhaps, you might be interested in what the acceleration is. And under those circumstances, suppose the acceleration turns out to be 9.8 meters per second. Aha! The moon landings were faked. Well, if you actually analyze those videos, you find out the acceleration is close to 1.6 meters per second squared. Things are not falling quite the same way on the moon as they do on Earth, so maybe that's not what you're looking for if you're a conspiracy theory-minded person. But this might provide some useful insight, long story short. This is much, much less than the acceleration due to gravity, so perhaps we're meaningfully on the moon. Now, the model reproducing the data set here means we have a model that could be used to calculate equivalently y given time. What that might look like, given a more concrete notion of what the data set looks like, is to, well, plot height versus time for the projectile motion case. Might look something like this. Got a randomly generated data set here. The points are not all following a perfectly smooth curve because there's some uncertainty in the data. That uncertainty is reflected in the error bars. Now, if you don't have an idea for what models to use, you can certainly try some. Perhaps you think a line would fit here. And you can put a line on top of your data set, and this is a reasonably good fit to the data, but obviously below the line, above the line, below the line, something's going on here. A line is not a very good fit here. Now, if this is projectile motion, you probably wouldn't even bother trying a line. You would go straight to a parabola and try and fit a parabola to your data. So it's reasonable to expect that this would fit better, and indeed it does. So this is a good fit. This is, in fact, the best fit. But what do we really mean by best fit? What do we mean by fit, exactly? We need some notion of what it means for a curve to reproduce data. The data is not all perfectly lying on the curve. Some data points are off by more, some data points are off by less, but it does sort of generally go through things. Well, what do we mean by best then? Let's try and make that concrete. One common way of specifying precisely what we mean by how well a curve goes through a set of data points is by computing something called the chi-square statistic and working with that. Now, the chi-square is really a measure of deviation between the measurement and the expected result based on the model. So if we're looking at a plot of y as a function of x, perhaps, let's take the crappy linear fit, for instance. If these are my data points, and there's some uncertainty in those data points, if I make a linear fit to the data, let's say I make a really bad effort at making a linear fit to the data, that model obviously doesn't work very well. It doesn't fit. Well, the chi-square statistic is based on consideration of how much these points deviate from the model. This one's above, this one's above, this one's above, these two are below. How large are these deviations on average? The actual computation is fairly straightforward. What you're doing is you're computing the deviations, and you're summing the squares of the deviations. We square them because if they're positive or negative, we can't just add them up. Positive would offset negative under those circumstances. But if you square them first, you get some measure of the size of the deviation of all of those points from the line. The smaller that sum is, the better. Now, in order to make this work accurately, we have to ensure that the data points that we are more certain about are taken more seriously in this sum. We have to account for the uncertainties. For instance, suppose I have another data point. It's way up here, but it has an enormous uncertainty associated with it. This deviation, despite the fact that it's relatively large, shouldn't count as much as this deviation. Despite the fact that the deviations are about equal, this point has a smaller uncertainty than this one. Now, the way we actually do that, the way we account for uncertainties in physics is usually by, well, calculating some error bar, measuring some sort of standard deviation or some uncertainty in the measurement. But once we've done that, if we've accounted for those uncertainties accurately, really what we mean by best fit is to minimize this sum of the squares of the deviations. The fact that we're squaring this means this minimization process is sometimes called least squares. And there are lots of versions of least squares. The version that we're talking about here is chi-square, since we're properly accounting for the uncertainties in each data point. So if we have some measurements, just to give us some notation, let's say I have y sub I plus or minus the uncertainty sigma of y sub I. If we make the assumption that on average the true value of these data points is going to be given by the model value, the true value y sub I, with some standard deviation sigma of y sub I, if we're going to make that assumption, that on average these things are okay, then this sum over all the data points of the deviation y sub I minus what we expect to get from the model, this is our model, some function, which probably comes from x sub I, some measurement of the, well, time, if we're talking about projectile motion, x in this sort of more general case. That's our deviation. We can correct for the uncertainty in the measurement by scaling this deviation by the measurement, and square the result, subject to the assumptions that are underlying chi-square minimization, namely that on average y and the expected value will be more or less on top of each other, and that the uncertainties are normally distributed. then this sum is the sum of a bunch of squares of normally distributed numbers. The relatively large deviation here might only be less than 1 standard deviation away. It would contribute less than 1 to the sum when we square it. But if these things are normally distributed, then the resulting statistic is what's called chi-square. Chi-square being defined as the sum of some n normally distributed random variables. So these things being, let's just say, z, where z is defined as some standard normal random number, will have mean of 0 and standard deviation 1 if we're looking at our deviations as scaled by the standard deviation estimate based on our experimental observations. So, subject to this assumption that the deviations are on average 0 and that the standard deviation is an honest estimate of the uncertainty in our number, these should approximate standard normal random variables. Summing them up after squaring them gives us something that's chi-square. Chi-square is, as a term, something that you can go and talk to your statistician friends about, and they'll tell you all sorts of nice properties of what the chi-square ought to be. For instance, if you sum up chi-square over n data points, if you're scaling things correctly, typically this chi-square will be approximately equal to the number of data points you have. This allows us to infer some characteristics of our fit. For instance, if you calculate chi-square and it turns out to be much, much greater than n, you've got a bad fit. Your line may seem to be going through your data points, but it's not going through them well enough. And this could mean that your uncertainties are too small, or it could mean that your model is wrong. On the other side of things, it's entirely possible that your chi-square will turn out to be much, much less than n. Now, under those circumstances, your uncertainties are all, the line is going through all of your error bars under those circumstances. That's, a relatively common outcome in experiments, and what that means is that your uncertainty estimates are wrong. Your error bars are too big. Your measurements might actually have been more accurate than you thought they were. Now, the process of minimizing chi-square then typically means you're tuning the parameters of your function, trying to make this chi-square number calculated as small as possible. What does that process look like? Well, let's suppose, just as an interactive sort of demonstration here, here's the data set, and here's an estimate of what the parabola might look like. And I have some initial position, initial velocity, and acceleration parameters that I can play with here. For example, if I move the initial position upwards, maybe that makes things better, maybe that makes things worse. And chi-square now is about 220. So if I'm tuning this parameter up, chi-square is getting bigger. If I move it down, chi-square is getting bigger again. There's a happy medium in there somewhere. But I have more than one parameter that I can tune here. I also have the initial velocity, and I have the acceleration. Large negative acceleration, small negative acceleration. And if I tune these sorts of things, this is actually not looking so bad. If I move things down a little bit more, okay, chi-square is down to 37. This is not a terrible fit. I expect chi-square to be, in this case, I have 20 data points. I expect chi-square to be about 20. 37, well, that's a little bit bigger than 20, but not horrible. And it looks like I'm actually doing a pretty good job at the beginning. But it turns out that you can do better here. If I make the acceleration a bit higher, make the initial velocity a little bit higher, overshot. Now we're down to 33 for a chi-square. This is starting to look like a pretty reasonable fit. Now, obviously, this is a very tedious process, and we don't want to have to do this by hand. But thankfully, well, obviously, the computers can do this for you. This is a tedious, sort of repetitive, guess and check kind of process. Computers are pretty good at that sort of thing. And there are actually some very clever algorithms for figuring out how to actually do this. So, what does this actually look like in Python? Curve fitting in Python requires a couple of pieces. First of all, it requires a model. We have to tell Python what mathematical function we're fitting to our data set. This is Python syntax for defining a function named model. And that model, as a function, takes 3 arguments. It takes some x-coordinate. This is going to be our independent variable in the sense of this as a function. And it takes some extra arguments that in this case are going to be parameters of the model. We just have to return the result of evaluating that model, and in this case it's a very simple mx plus b kind of thing. M is the slope, b is the y-intercept. So this is what fitting a line to your data set looks like in Python. Now, the actual act of fitting the curve is handled, perhaps unsurprisingly, by the curveFit function. This is in the scipy.optimize sub-package that must be imported first. But what curveFit does is fit your model to your data. So what does it need to do that? First of all, curveFit needs your model. It needs your data, which in this case I'm assuming is stored in a pandas data frame named D as the time and position columns. You give it the independent variable first, and then the dependent variable second. curveFit also needs some estimate of the uncertainties because it needs to calculate an honest sort of least squares, chi-square kind of statistic. So you need to give it the sigma argument, which is the uncertainties, which I'm calling s underscore position for the uncertainty sigma in the position variable. So if we give it the model, the data, the uncertainties in the data, we're almost there. And we need two additional things. First of all, curveFit needs to know where it should start hunting. What are reasonable values for the parameters? So I'm giving it this initGuess parameter, where initGuess is just a list of two entries, just 1 and 1. Start at slope 1, y-intercept 1. These are going to correspond to the slope and y-intercept of that function. So I give it the initial guess as the p0 argument, and it also can calculate the chi-square statistic in a couple of different ways. The absolute sigma equals true option specifies that I'm actually trying to make these uncertainties in positions true standard deviations. I'm trying to do chi-square analysis correctly, in other words. If you don't say absolute sigma equals true, it will still give you an answer. It will try its best to estimate things. And if you don't give it an initial guess, it will still try. It's just going to use ones for the initial guess, which is the same as what I'm giving it here anyway. So this would have worked regardless. But you do, in general, want to give it an initial guess, as well as an absolute sigma. What curveFit gives you, then, is this fit thing. I'm just declaring a variable named fit to capture the result of this function call to curveFit. What exactly is in that fit? Well, two things are in that fit. First of all, there's some answer that needs to be unpacked. That's going to, if we unpack the answer further, give us a fit result for the slope and a fit result for the intercept. It's also giving me something called, I'm calling cov here. That's short for covariance, and we'll come back to that later. This is going to be how we ascertain the uncertainty in the fit results themselves. So that's fitting a line to the data set. But what if we don't want to fit a line to the data set? What if we want to fit something slightly more complicated to the data set? Well, that requires some changes. First of all, if we're fitting a parabola instead of a line, we need our model to reflect a parabola. So if we're doing the projectile motion example, perhaps we have an initial position, an initial velocity, and an acceleration. And we have three parameters for our model. It's a new model. And it's going to take the form of y plus vt plus 1/2 at squared. Typical parabola form that you might get from, well, first year physics. We need to give it a new initial guess now since we have three parameters. So let's say the initial velocity is, or initial position is 1, the initial velocity is 1, and the initial acceleration is minus 10. Perhaps we think it's on Earth, so the acceleration ought to be minus 10 meters per second squared. And then when we call curveFit, nothing really has to change. We're still giving it the model, which is now this new model involving the parabola. We're giving it the time, the position, the uncertainty in the position as sigma, the initial guess as p naught, and, well, true as absolute sigma. And you're running the fit the same way. You also have to change the way you unpack the result. Fit still gives you some estimate of the best fit parameters for y, v naught, and a, and some covariance. But you have to unpack the answer into three pieces now, since I have a fit result for y naught, a fit result for v naught, and a fit result for the acceleration. So changing the model means changing the model itself, of course, changing the initial guess, and changing the way you unpack the model. So if we're messing around with models, which you'll end up doing quite a bit, tweaking the models, tweaking the initial guesses, those are the sorts of things that you'll end up changing quite frequently. So once you've got your fit done, what do we do with it? Well, we need to plot the results. Plotting fit results in Python actually takes more code than actually executing the fit. But we're working with matplotlib now. Starting with the part where we unpack the fit results, we need to plot this in a couple of different ways. First of all, you need to plot the data set. That's typically done with this error bar sort of command. So this is your data. The error bar command takes a couple of arguments. It takes the time, it takes the independent variable, the x-coordinate. It takes the y-coordinate, and it takes the uncertainty in the y-coordinate as the first three arguments by default. I'm giving it a format to use blue dots as a useful shorthand. You can change the character to signify different colors and change the marker style if you want. And I'm giving it a label that will be useful when we put a legend on the plot later. I'm also labeling the axes, of course. This is as good a time as any to do that. If you just do this, this will result in that error bar plot that I showed you at the very beginning of this lecture, just showing the data. We also want to plot the model on top of itself, or on top of the data, hopefully to see that the model in fact does go through the data points and makes for a good fit. But the model, however, now is a mathematical function. And mathematical functions, well, while these commands that exist in matplotlib, like plot or error bar or lines or whatnot, well, they plot data sets. They don't plot mathematical functions. So we need to make a sort of pseudo data set so that we can plot our model exactly. One good way of doing that is with the linspace command. So I'm making a dummy variable t here to store uniformly spaced points between 0 and 2. That's what linspace does. By default, it gives you 50 of them. You can ask for more if you like. Plotting that model then means using that dummy set of x-coordinates, pseudo times, if you want to think of them that way, as the x-coordinates in your plot. As the y-coordinates in the plot, then you want to use the evaluation of the model. So use the model, use your fit results, fit h0, fit v0, fit a, these things that we, oops, this is a typo, this is supposed to say h0. Use those things that you unpacked from the fit results as arguments to your model, and, well, make a plot. So t here is coming from this t, so we're using our x-coordinate, and then we're using our model as a function to compute what we would expect at all of those hypothetical x-coordinates. Again, giving it a label, and let's put the legend on now. This is as good a time as any to do that. So this is your plot of the model, which hopefully goes on top of the data. Now, as an additional diagnostic, this is as good a time as any to compute the actual chi-square statistic. Curve-fit doesn't give you this for some reason, but the chi-square is easy enough to calculate. What computing the chi-square looks like in this context is, like I said, it's summing up the squares of the deviations between the data and the model. So the deviations between the data and the model means looking at the data, subtracting what we would expect to get from the model. This is data minus model. The model now, instead of evaluating it at all of the dummy coordinates, I only need to evaluate it at the coordinates that actually exist in the data set. So I'm going to use the time column from my pandas data frame as if it were the time argument in the function for the model. I'm going to use the fit results as the additional arguments for the model. So this is observation minus model expectation. Now all of that is in parentheses here, divided by the uncertainty in the position, and all of that then gets squared. So this is observed minus expected, scaled by the uncertainty, quantity squared, summed up. That was the definition of the chi-square test statistic. Now, just for the sake of making things pretty, I'm going to put the actual value of the chi-square on the plot using the figtext function. These are relative coordinates in the figure. You can tweak them if you want to move where the words chi-square appears. And then this is just shorthand for plotting in a nice string form chi-square, and then the value of chi-square, this percent thing, will be replaced by the value of the chi-square variable. %.2f signifies floating point, 2 digits of precision, so it will format things nicely. And make it bold, why not, just to make things pretty. If you go through that, this is what you actually get as your final result. That's your fit result. And your best fit here, under these circumstances, actually comes out quite low, 22. We expect chi-square to be about 20. This is more than fair. That's a very good chi-square value. It's exactly more or less what you would expect. Because chi-square is not always going to be exactly 20. It doesn't have to come out exact. So this looks pretty good. As fit results go, this is more or less what you want to see. But in general, when you're making a curve fit, you also want to plot some notion of how much deviation you actually have to see if there's anything that's not quite captured by your model. And one way of doing that is to make what's called a residuals plot. Now, a residuals plot in Python looks something like this. Let's make it as an error bar plot. We're going to use the x-coordinates from the data set But then as the y-coordinates, we're replotting the data set, but instead of replotting the data set, we're going to subtract off the model. Now, if I flip back a slide, what that means is that the y-coordinates that I'm using on my plot will be the deviations between the data set and the model evaluated at that corresponding x-coordinate. So this point would have a relatively large positive residual. This point would have a relatively large negative residual. If I plot these residuals and I can see something funny happening, well, then I know something is wrong with my fit. So we're basically replotting the data set, but instead of the data just by itself, you're subtracting off the model fit results, evaluated at the locations of the data set. So again, x-coordinate, y-coordinate, now with the offset, and the uncertainties, as necessary for the error bar plot. But what we expect now is that our residuals should all average 0. So I'm going to use the hlines command here to plot a horizontal line at y equals 0, ranging from 0 to 2. Those are characteristic times for the system that I was working with here. And then let's label it. Now what the residuals plot actually looks like is something like this. So this was that point that I pointed out earlier that had a relatively large positive residual next to a point that had relatively large negative residual. This is what a residuals plot ought to look like. It shows you basically nothing. Some of your points are beyond, like the error bar for this point is not going through 0, meaning this point is more separated from what you would expect from the fit results than its uncertainty typically would allow. But most of the points do. This guy, this guy, this guy, this guy, this guy, this guy, they're all fine. They all have uncertainties that put them within one uncertainty of 0 residual, meaning less than one uncertainty from the fit result. The error bar goes through the line. The residuals plot, in some sense, flattens out the fit result to be at y equals 0. It's the height observed minus the height fit. So is this a problem that this point is way off here? Not really. In physics, typically the uncertainties, the error bars that we assess when we're doing experiments, we estimate them as one standard deviation, 1 sigma uncertainties. And 1 sigma uncertainty, well, if you randomly draw normally distributed random numbers, they will be more than 1 standard deviation from 0, roughly 30% of the time, about a third of the time. So if a third of your data points don't have error bars that go through the line, that's okay. If like most of your data points have error bars that don't go through the line, then, well, that's a problem. For instance, here's what the residuals plot looks like if I do a linear fit. Obviously, a line doesn't fit a parabola very well, and, well, most of the data points now fall more than one uncertainty away from 0 residual. So that's kind of bad. Another thing that's bad about this, and this is really what you should be looking for when you're making a residuals plot, is a trend. There's a very clear parabolic trend in this residuals plot. So while the physics you might expect the physics to tell you that perhaps the height ought to be a linear function of time, the fact that there seems to be a curve in the residuals plot here, well, that suggests that your model is not quite accurate, that there's some parabolic behavior that's not captured in your model that really ought to be in order to adequately fit the data. Now, small deviations in the residuals plot from the expected trend are generally okay, especially if they're within chi-square, because of all the effects that we don't often consider in physics, things like air resistance and whatnot. So that's the chi-square, or sorry, that's the residuals plot. But let's go back to the best fit here. This was our best fit. This is a good fit. Chi-square of 22.8, when you expect chi-square to be about 20, that's good. But we don't expect chi-square to be always exactly 20, and 22.8, 22.9 is actually pretty close. So what about all these other fits? Now, a whole bunch of other fits which are candidates. They're pretty close. They also seem to go mostly through the data points. If you compute chi-squares for these other curves, these chi-squares values range from about 23 up to 28. So our best fit chi-square was 22.9, 22.88. These are starting at 23 and going up to 28. Not terrible. Not bad, but not the best. But they're actually technically okay. And the reason for that is that, statistically speaking, if you add up a bunch of random normally distributed values squared to compute chi-square, or something like it, you're not going to get 20 all the time. Sometimes you're going to get something larger than 20, in this case with 20 data points. Perhaps you'll get 30. Maybe 30 is not so bad. Maybe 30 is expected. That's not too far off. What's nice about this is that knowing the statistics, assuming these things are random, normally distributed around the fit results in some sense, means we can use what we know about chi-square to assess how these points are likely to fluctuate if we repeated the experiment, which is going to allow us to infer an uncertainty in the fit results themselves. So if I get a fit result, I can judge its uncertainty by looking at how these fit results are likely to vary subject to the known size of the error bars. This is why we pass the true argument to absolute sigma when we're calling curve fit. Now, curve fit's other argument that I alluded to earlier, the fit results can be unpacked into the best fit value of the parameters and the covariance. And the covariance is what tells us about the uncertainty in the fit results. So let's take a step back and talk about variance and covariance and what they mean so that we can actually interpret that. First of all, if you've got some sort of data set, let's just say we're talking about x and y. We have n data points, let's say x1, x2, x3, etc., y1, y2, y3, etc. You can make some computations of, well, characteristics of this data set. Like the mean, perhaps. The mean of this data set is defined as 1 over the number of data points times the sum over all of those data points. So if I'm adding up x sub i's, dividing by the total number of data points, I'm going to find the mean value of x. Now, another statistic that's very common to calculate is the variance. The variance is usually denoted by sigma squared. So if I'm computing the variance of x, what that means is I'm computing 1 over the number of data points. I'm dividing by the number of data points, and I'm again summing over all data points, but what I'm summing is the ith data point minus the mean, and I'm squaring it. So if your data set, let's say I've got some x-axis here, if your data set falls, all over the place, some points are way out, some points are clustered, the mean might be, I don't know, here. What the variance here computes is, well, xi minus mu. If this is the point I'm considering, I have some deviation, squaring the deviation, and then dividing by the total number of data points. This is the mean squared deviation. I've got a whole bunch of deviations here, some of them positive, some of them negative. This is going to give me a characteristic sort of spread in the data set, or some characteristic deviation. Now that's the variance, the characteristic deviation from the mean squared. Now the covariance is a little bit different. The covariance, if I'm talking about the covariance, now I'm talking about two different variables, potentially, the covariance of x and y. Might be defined, or is defined, in fact, as something that looks very similar to the variance, where again, 1 over n, sum over all the data points, but what we're summing is now x sub I minus mu sub x multiplied by y sub I minus mu sub y. So it looks a lot like the definition of the variance, but instead of having x minus mu quantity squared, I have x minus mu, y minus mu, the mean of x and the mean of y being used respectively. This tells me the extent to which x and y tend to vary together. For instance, if when x is greater than its mean, this is positive. If that tends to go in your data set with y values that are also larger than that mean, then this product will be a positive number times a positive number. It will tend to be positive, and your covariance will tend to turn out to be a positive number. Now, if when x is larger than its mean, y tends to be smaller than its mean, then this product will turn out to be negative, and you'll get a negative covariance. So this covariance thing tells you the degree to which x and y tend to vary together, and it's related to the variance. If you want to think about the variance in x, this is another common notation for sigma x squared. The variance of x is really the covariance of x with itself, because that would replace the y's with x's in this expression, which would make it identical to that expression. What this really looks like, if we had a couple of characteristic covariance values, if our data set in terms of x and y looks, I don't know, something like this, with points more or less scattered all over the place, we have as many cases where, let's say, the means are at 0, where the x-coordinate is positive and the y-coordinate is positive, as x-coordinate is positive and y-coordinate is negative. Things don't seem to be particularly aligned. Your data set is more or less falling inside a circular sort of region. This would be our low covariance case. Covariance would be close to 0. High covariance, by contrast, our x and y coordinates of our data set might look something like this. That if you were trying to enclose most of your data points inside a circle, well, you'd really want to use an ellipse. This would be the high covariance case. When x is positive, above the mean, y tends to be above its mean. When x is negative, below its mean, y tends to also be negative below its mean. And the case where x is positive but y is negative, or x is negative but y is positive, tends to be relatively a small fraction of the data points. So the average of this quantity is going to be positive contributions from both, negative contributions from both multiplied together to give you something positive. This would be a high positive covariance. Now, what's nice about covariance in this context is that curve fit provides an estimate of this. This is really handy because this allows us to estimate the uncertainty in our fit results. Because what curve fit provides an estimate of isn't the covariance associated with our data, it's a covariance associated with fit results. So it's the covariance of the fit results, meaning what I really ought to be looking at in this context isn't correlations between, say, time and height, but correlations between something like slope and intercept. So we're taking a step beyond the data set here and talking about the results of the fit. And curve fit's telling us something useful about that. Now, what makes covariance a little bit difficult to estimate or to interpret is that what the curve fit function actually provides is an estimate of the covariance matrix. Because we have multiple fit parameters, we're going to have like the variance of x with itself, the variance of x with y, an estimate of the variance of the intercept perhaps, an estimate of the variance of the slope, and an estimate of the covariance of slope and intercept together. We'll talk about how to interpret those things in general. So what does it mean? What does the covariance actually look like? Well, first of all, it's a matrix. So if I'm talking about something like slope and intercept as our fit parameters, what I'm going to get from curve fit is an estimate of the covariance matrix. If the slope is the first parameter, this would be like sigma slope squared, the variance in the slope, an estimate of the uncertainty in the fit slope. The lower right element of the matrix is going to be an estimate of the variance in the uncertainty, in the variance of the intercept, an estimate of the uncertainty in the fit result intercept. And then the off-diagonal elements are going to be the same. This is going to be a symmetric matrix. But what this is telling you is the covariance of the slope and the intercept together. Now, why would the slope tend to be large? Why would we ever have a non-zero covariance between these fit result parameters? Well, if you can compensate for a bad slope by changing the intercept. A situation where this happens would be perhaps you're fitting a line to a data set, and your data set's all over here. Now, what your best fit curve might look like is something like this, line pretty much going through the data set. But if I make the slope lower, if I make this curve flatter, I can go through the data set more or less as okay, provided I shift the intercept up. So if I bend the slope down but shift the intercept up, I can compensate for the badness of the fit, at least partially. That would give me a covariance here that was non-zero. So first of all, looking at a covariance matrix, the diagonal elements tell you the variance of the fit result. The best fit parameters, it gives you an estimate of the uncertainty. And that's pretty easy to unpack. You have a covariance matrix. There's a diag function in Python that will pull out the diagonal entries of the matrix. And of course, there's the square root. So you're taking the square root of the diagonal elements is telling you the fit standard deviation sigma, not the variance, sigma squared, but the standard deviation sigma of the slope and the standard deviation of the intercept. The off-diagonal elements, like I said, are related to how these fit parameters are coupled. If I can improve the fit with a bad slope by changing the y-intercept. Now, if this is very large compared to your diagonal elements, if your fit parameters are tightly coupled, if the covariance is very close to or comparable to or even larger than your variance of your parameters themselves, well, then you've got a problem and you need to consider rewriting your model. So what does that look like? Well, here's the covariance matrix for the parabola fit that I was showing you earlier. So the parameters that we were looking at under those circumstances, the columns and rows of this matrix correspond to the initial height, the initial velocity, and the acceleration. So the diagonal entry here, this is the square of the uncertainty of the initial height, this is the square of the uncertainty of the initial velocity, and this is the square of the uncertainty of the acceleration. Now the off-diagonal entries, in particular these, are comparable to the value of what's going on the diagonal. That means these fit parameters are tightly coupled, and we ought to think about this fit, think about it a second time. Another way of looking at this covariance is to compute what's called the correlation matrix. Now, the correlation coefficients, which you've probably heard of from the perspective of how good a linear fit is telling you, again, the correlation is just calculated from the covariance. The correlation coefficient between two variables, x and y, or two data columns, x and y, is the covariance of x and y, just divided by the square root of the variance of x and the variance of y computed separately. So it's basically a normalization of the covariance. In this case, the fact that these numbers are so close to 1, where something is perfectly correlated with itself, this is a very high correlation coefficient, meaning that these fit result parameters are expected to be tightly coupled. And that's actually something that you can see. Now, since I'm doing this for demonstration purposes on the computer, I have the luxury of going back and repeating the process many, many times and figuring out how the fit results are actually varying. If I do that, this is what I get. This is your fit result for acceleration plotted versus the fit result for velocity, now looking at many, many, many trials of this experiment. And this is a fairly linear plot. It's got a negative slope, which means if I wanted to, for instance, make the acceleration more negative, go from, like 9.8 up to minus 11, or g of minus 9.8 to minus 11, I can compensate for that by increasing the fit velocity, or the best fit velocity. Now, if the initial velocity best fit is like 11, I can push that up to 12 or 13 in exchange for having the fit acceleration be minus 10 instead of minus 9. These fit parameters are coupled together. Now, your uncertainty estimates are still okay under these circumstances. You have some notion of the uncertainty in the acceleration. You have some notion of the uncertainty in the initial velocity. These are your variances. These are your diagonal elements, or can be computed from your variances. They're the square roots of the variances. That's what you want to use for your uncertainty. But under these circumstances, things are tightly correlated. So let's see how we can improve that. Really what we want to do here is make our fit parameters more independent from one another, which really means, well, like I was talking about earlier, if we have a linear fit, we have really two parameters here. We have a slope and we have an intercept. Shifting the intercept means moving everything up and down, and shifting the slope, well, that means changing the slope like that. Now, this is the case for if I'm writing my fit function as just something simple. In this case, it's like y equals mx plus b. This is what happens if I change b. This is what happens if I change m. Changing the slope does not change the intercept. Changing the intercept does not change the slope. But I can combine these two parameters together a little bit. What if, instead of making my fit function expressed simply, I made it expressed as y equals m x minus x naught, some characteristic x value, plus b, and I can offset on b as well, for some characteristic b value. So x naught and b naught here, these are just constants. They're something that I am going to set. And I'm going to set them such that they're more or less at the center of the data set. For instance, if I'm trying to fit a data set off here, if I choose this as my x naught value and this as my b naught value, my characteristic height and characteristic horizontal position of the data set, what I will get under these circumstances is a line, the corresponding plots for changing b and changing m would look something like this. Changing b is still going to shift everything up and down, but changing m now will be shifting things like that around perhaps the center of my data set. So if my data set is over here, centered around where I chose for x0, then changing the slope doesn't move everything up and down. If my data set is, over here, changing the slope moves my curve up and down. Changing the slope now does not move my curve up and down. That's one way you might retool a linear fit to avoid possible correlations between slope and intercept. Now, in the context of the curves that we've been working with here, I'm going to shrink this down to buy myself a little more space. If we're talking about a parabola, that was the case that we were considering. Y equals h0 plus v0 t plus 1/2 at squared. We can write that differently. This is just a generic parabola, ax squared plus bx plus c, with time used for my x coordinate. I've got any three parameters that I can put in a parabolic function can potentially make this work. So what if I considered something like, I don't know, a times x minus b quantity squared plus c. Now I have something that's going to end up in the end multiplied by x squared. I don't have an explicit slope parameter anymore. I have, in some sense, where the center of the parabola is. X minus b, when x is 0, that's going to be where the parabola is at its peak. So I have now a peak location, a width, and an overall height sort of parameter. That's the interpretation that you'd have there. But that's not the end either. I could say, what if y were equal to, let's say, x minus a, x minus b, plus c, or sorry, times c. This would be one root of the parabola, this would be another root of the parabola, and this would be some notion of the sharpness of the parabola. These are all, parabolic models. They're all potentially as good. Some might work better than others. But let's try this one. Since I know in some sense that I have a parabola peaking at a particular time, this will shift my parabola back and forth. This will change its sharpness. This will change its height. Let's work with the revised parabola fit. Now, if you do that, the covariance you get improves substantially in the sense that while the diagonal elements aren't directly comparable anymore because we have different parameters in use, the off-diagonal elements are now substantially smaller than the on-diagonal elements, at least relative to what they were before. If you compute the correlation matrix, which, since it's normalized with respect to 1, is relatively easier to look at, 0.73 now is our largest correlation. 0.61, 0.21, those are smaller than what they were before, which is a good thing. And if I again repeat the experiment many, many times, repeat the fit many, many times with the new parabola, and plot the most highly correlated values, in this case acceleration versus the time of the peak, that b parameter that shifts the parabola left and right, now you get something like this. It's still correlated, but it's not as correlated as it was before, and that's reflected in the off-diagonal entries being smaller in the covariance matrix or the correlation matrix. So if I go back and do the same fit, I end up with the same fit result. The changing form of the fit function doesn't actually change things all that much, but in the end, we do end up with a better sort of covariance. So to sum up at the end, at the beginning of the data analysis process, you have to have some data to work with. That means you're collecting something from observation and experiment. What we're ultimately hunting for in the end is a model that's expected to reproduce some feature of the data, and we can construct that model reasonably easily, especially for simple physical systems, by curve fitting. What that means is matching a curve to a plot of the data, and a very common and very versatile and very powerful way of doing this is by minimizing the chi-square statistic. Curve fit can do that for you. It needs the model, it needs an initial guess, and you need to unpack the results and interpret them meaningfully. You also need to calculate the chi-square, and the chi-square should be roughly the number of data points, approximately. If it's too big, bad model. If it's too small, bad uncertainty estimates. The plot results, you also have to plot the results of your fit, of course. Use error bar for the data. Plot the model on uniformly spaced points overlapping with the data. Construct something with linspace for that, but just use plot for that. That's a line. The model's generally not anything fancy. Don't use the data to evaluate your model, because oftentimes things will end up out of order that way. You'll see what happens if you do it, but use linspace, and make a residuals plot. The residuals plot should show no obvious trends and not have any horrific outliers, though it's not that much of a problem if around a third of your data points fall larger than the error bar distance away from the 0 line on the residuals plot, meaning that a third of your data points, up to a third of your data points, is more than one uncertainty from the fit result. Finally, interpreting the covariance estimate allows us to estimate the uncertainties in the fit result parameters, the actual best fit results. The square root of the entries along the diagonal gives us an estimate of the uncertainties. So for instance, if our best fit acceleration for the parabola fit was something like 10, that would be 10 meters per second squared perhaps. The square root of the diagonal entry corresponding to that fit parameter in your model, say it's the third parameter to your model, it would be the third column and third row of the covariance matrix. The third diagonal entry then would correspond to the square of the uncertainty. You can compute the plus or minus the square root of that number along the diagonal of the covariance matrix as an estimate of the uncertainty in the acceleration. And keep an eye on the off-diagonal entries as well, because they're associated with correlated errors, that if you have large variances in one parameter, it means it potentially is contaminating other parameters by causing them to vary as well. But that's curve fitting in a nutshell. We're overall plotting something and making a line appear on top of that, but what we really care about in the end is the fit result parameters and how to interpret them. So I hope this walkthrough, including code, gives you a starting point for fitting curves to your dataset.